Welcome back, everybody. And we continue our discussion of aromaticity. Aromaticity contributes towards the stabilization of pi electrons when molecules are aromatic, and as a consequence, contribute towards their lack of reactivity under normal circumstances that we have seen before. For example, in section 6.1d, we did the bromination of alkenes, and we learned this reaction was very fast. Very fast. Happens within seconds. We try the same reaction with benzene, and we get absolutely nothing. Why? Because the pi electrons in benzene are resonance stabilized by aromaticity to the tune of 152 kilojoules per mole for 6 pi electrons. Not reactive enough. In our next chapter, which will focus exclusively on reactions of benzene, we're going to see that you can force the benzene to react, but it will not be in a fashion such as it was in section 6.1d. It will be a substitution reaction where this H here gets replaced with a bromine. And I found a typo. This should be HBr here. It's a side product. I am not going to become overly fixated with that typo. There's going to be other groups in chapter 22. Might as well do a little heads up. We'll be able to put a CL on there too. We'll learn how to put a nitro group on there. That's our new group we just talked about. We'll learn how to put a sulfonic acid on there. So by the end of chapter 22, we'll learn how HOTS is made. Put a line in front of each of these groups. That's the bond to benzene. And what else are we going to learn? Our special R groups. That's alkyl. And see who remembers what it's called when we have carbonyl attached to R. I'll give you a couple seconds here. Carbonyl attached to R is not an alkyl. That's called, what's it called? Do you remember? It's called acyl. We're going to learn how to acylate benzene, alkylate benzene, sulfonate benzene, nitrate benzene, and chlorinate benzene. And in chapter 23, we'll learn a couple more things about putting groups on benzene. But that's a good start for us right there. Anyway, we're not even going to do it today. So looking ahead and coming back to reality, we have the Claisen rearrangement here. And yes, it's the same dude, Claisen. He has two reactions. Good for him. This one is not a condensation. It's a rearrangement, and it takes advantage of groups being tethered to benzene in an ether. And it can't be just any old group attached to benzene in an ether. It has to be an allyl ether of some variety. So reminder, putting allyl groups on benzene is not that difficult. We can take the H off of a phenol, pKa 10, easily removed, as we saw in our last test with the acetoacetic ester synthesis and malonic ester syntheses. Just use hydroxide, take the H off. Now you have a nucleophile. It's going to do an SN2 reaction. Got the SN2 reaction down here. And the simplest allyl group would be allyl chloride or bromide. Then you have an allyl phenyl ether. And what happens after that is you simply heat this molecule. And no other chemicals are added. What you get is a mechanism that looks a lot like the resonance of benzene itself. We'll put it here. I want you to look at the arrows in the simple resonance of benzene. And I want it to match. I don't think I should have started with that benzene. Oh, sneaky. I just want it to match with the arrows that I see there on the screen. I can resonate like that. And then this one resonates to there and resonates to here. And we get equal resonance structures, 50-50. And don't these three arrows look the same as these three arrows? When we do these three arrows, but this is a chemical transformation. Do you know how I know that? It's not resonance. Do you know how I know? The formula of the molecule didn't change, that we don't call that a reaction. Oh, we do call it a reaction. We made a new sigma bond from here to here. We lost sigma bond here. Anytime you break sigma bonds, that's a chemical change. So reactions that where the mechanism looks a lot like benzene's resonance, they have a name. And it's a good name. I like this name. The mechanism arrows go around a ring. Peri, like periphery, around the periphery. Cycle, clearly, they're going around in a circle. And it's a reaction because we're making new sigma bonds, breaking old sigma bonds. And we get our old friend, carbonyl. And usually this kind of reaction, the reaction that goes from a carbonyl to an enol normally favors the carbonyl. Can I remind you why? The carbonyl is normally favored because the pi electrons to an oxygen are stronger than the pi electrons from carbon to carbon. That's normally the case for a tautomerization, which is what we just saw here. Why does this tautomerization favor the enol form? What's the title of the chapter? Aromaticity. This molecule you have here is not aromatic for one simple reason. In the ring, you have an sp3 atom. An sp3 atom cannot resonate in a circle. But after you make the enol tautomer, which is the resonance of the tautomer form, of the ketone, is the enol. It's not resonance. It's a reaction as well. This form can resonate in an aromatic fashion. So why don't we try our own version of this with a more interesting molecule? Let's try this one. And let's do this. And we'll have a double bond here. Cl here. And I'm going to react that with NaOH. And we're going to make an intermediate here. And what's it going to look like? It's going to be an ether, where we end up with a C attached to a C. The C has an alkene over here. And this C used to have a chlorine, and now, ooh, this is challenging my brain. 1, 2, 3, then the C with the Cl. This is the C with the Cl. 1, 2, 3. And then I'm going to heat that up. I may regret the fact I don't have a couple more C's in here. So I increased it by 1. Work in progress. This is what happens when you're making stuff up as you go. There. And the question is, and I'm not even going to try, I'm going to make this like a problem set. We're going to predict the product and give a mechanism. I don't do that to you on tests. There's double jeopardy involved. But my thinking on problem sets, you've got time to figure things out and get it right, and then do it from there. Okay, so I want to do mechanisms for all parts here. And I don't want to redraw molecules if I don't have to. So I'm going to show that bond there. And I'm going to steal the whole thing. And put it down here. Hope it doesn't get too small. Okay. Sodium Spectator, hydroxide anion. Mechanism starts simple. Red first. Blue second. And let's look up top. Acid base is followed by an attack of the anion on the carbon with a halogen. Okay, so acid base is followed by an attack on the anion from the O minus. Oops, not with a red arrow, it's not. That's a second step after you generate O minus. And here we go. We've got a phenoxide. Do we have what's in the box? We do. We have what's in the box. I don't have to draw anything. Let's see. Call this A, B, C, D. A, B, C, D. Then the C with the allele. Then the C with the allele. Or I guess you call it vinyl. Sorry, it's vinyl. It's an allele ether up here because the oxygen's off this carbon one away from the alkene. And I think I have all the atoms here. Now on a test, you want to do the Claisen rearrangement, but you need the resonance form of benzene that has the pi here so that you can put the group there, ortho. Right here, I need the pi here to put the group ortho here. I can't put the group here. It just can't reach. This thing's out here. It can't reach over there. It's got to be in the middle here. So on a test, don't even draw the one you don't want. I need my surgical eraser. You don't even have to show me how to go from one resonance form to the other. Just draw the one you want. So carefully erase. Put the pi electrons back on where you want them. So when you're doing a Claisen, you want them like that with the new group going on this position of this pi, and that pi has the O on it on the other side. And then you can do the arrows at the top of the screen, magical pericyclic arrows. Oh, good, I can see everything. This pi breaks and goes where? To the distal end of the allele pi, like how I said that? The distal end of the allele pi. What happens to the allele pi? It becomes a C-double-C next door. What happens to the old CO bond? This would be the rate determining bond breaking here. You don't like breaking sigma. You are going to make a carbonyl, which is not a terrible thing. You're losing aromaticity. That is a terrible thing. That's why you need all this heat. You're losing aromaticity right now. We're about to predict the product, but we got to draw the ketone version first. Let's see what we got. It's exciting. Got a ketone. We have this old stuff here. Yeah, it goes up to here. Comes down to here. It doesn't have to be pretty. And it goes, I don't know, it's still not pretty enough. Doesn't have to be pretty, then it's not pretty enough. Make up your mind. Okay, so we're finished drawing up to here. I'm going to draw up to there. Try to take up a little less space this time. And then we have this. Thus, I'm not moving anything. We have a new bond right here. All right. We have a pi bond in here. And we have what else? That's it. All right. Pretty cool. I think that's it. And what happens in the last step? Oh, where you made the new sigma bond is here. On the same carbon, there's an H. It was there all along. That's why this thing's not aromatic. That H has to move. Where's it going to move? It's going to become an enol on the O. So draw me the H that has to move. There's no chemicals, yet you need to do a tautomerization. Driving forces, you're making an aromatic molecule. And yeah, somebody was going to say something. And thank you for holding off. We never touched that pi bond. We never touched this pi bond. Please don't. I was a little lazy on that one. There we go. We never touched it. Now we're going to do some intermol where the carbonyl grabs the H from some other species. Let's do it like we did previously. Just draw the arrow all the way to the H and just tell me you know that has to get it from a second molecule. And that's how you get your pi electrons for aromaticity back. And we never predicted our product, but we're going to now. Here's our product. What do we got over here? I don't have, how far can go to the right? Just worried about your notes getting too tiny. Squeeze that in a little. Final product. Put it right here. Got your phenol. Double, new double, OH. We have ring size, what over here? 1, 2, 3, 4, 5, 6, 7, 8. And 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we can just draw it like we see it, not worry about counting too much. CH2, CH2, CH2. I'm up to right here, coming up to a CH2, to a C, to a double C, to a bond, to a bond. And I don't know how this happened. Something moved when I wasn't looking, and this looks terrible. Okay. Okay, I erased it and it came back. That's what we get. And there you have it. Claisen Rearrangement. Lots of practice in the book on that. Please take advantage. And now we'll talk about the Colby synthesis of salicylic acid to close out this segment here. And Colby, not to be confused with Kobe, the basketball player. spelled similarly, except we have an L here. Colby, and this gentleman is responsible for saving the lives of many yew trees. And yew trees have salicylic acid in their bark. I think I have my trees wrong. Birch. How have I forgotten which tree has the salicylic acid in its bark? Somebody's going to research that for me. It's in my own book. I wrote it. But anyway, salicylic acid is an important pharmaceutical ingredient. One, it's used as an antiseptic all by itself. You'll find it in a lot of facial scrubs nowadays where it disinfects wounds and it penetrates through grease fairly well because it's not that polar. So it's an anti-acne preventative wash. It's also used as the active ingredient in compound W. Salicylic acid kills warts. Salicylic acid is the precursor to acetyl salicylic acid, where you put an ester here with an acetyl group, and that is the most used medicine in the history of mankind, called aspirin, acetyl salicylic acid. So I think my message that a salicylic acid is an important molecule has been made. If you had to isolate it from the tree, you have to strip all the bark off the tree because it's in the bark that the salicylic acid is found. And whenever you strip a tree's bark, the tree is going to die. So thousands of trees get killed every year to make salicylic acid or to extract salicylic acid from the bark. This does not need to be done if you start with this byproduct of the petroleum industry, phenol. You can take care of making salicylic acid by using the Colby synthesis. So Colby saved some trees. Once again, take advantage of the pKa of phenol being low, take its H off, throw in some dry ice. That's what carbon dioxide is in its solid form. Dry ice will react with the phenoxide, and it does a similar thing to the previous reaction, except this behaves like an enolate. It looks like an enolate and it's behaving like one. And it attacks at the alpha position to a carbonyl and makes a carboxylate. And then there's a lot of base present. There's an excess of base will cause aromatization by acid-base removal of this H to give this salicylate ion, which is the diconjugate base of salicylic acid. Why are these black arrows first and these gray arrows second? It's because the pKb of 14 minus 10 is 4. Remember, phenol's pKa is 10, and the pKb of a carboxylate is 14 minus 5, which is the pKa of salicylic acid's carboxylic acid portion. So 14 minus 5 is 9. 4 pKb reacts before 9 pKb every day of the week. And we have our salicylic acid produced by reacting byproduct of the petroleum industry, phenol, with fairly cheap chemicals, although a lot of specialized equipment is needed for this process. So I think that's a good stopping point for our third segment today. We'll come back after the break and finish up chapter 21, short chapter. See you shortly.